Hello, hello. Good afternoon. And good afternoon. All right. Hello, Paulina. Long time no see. Just kidding. Sort of. Okay. And good afternoon. All right, here we go. And there's Maria. All right. And there's a picture of Stephanie. Well, not of Stephanie. And a picture of Michelle Quach. Well, not really of, well, maybe. I don't think so. Okay. And there's Michelle F. Good morning, afternoon. And good afternoon, Katie. I said good afternoon, Brooke. Good afternoon, Jada. Good afternoon, Michelle F. Good afternoon, Marilyn CH. Good afternoon, Lena. Right. Good afternoon, Allison. Afternoon, Maria. I love how Maria withholds judgment on the actual. She's like, it's an afternoon. I'll go that far. Good afternoon, Fariel, who definitely wishes that I would take less time on these good afternoons. Right. And we will. Good afternoon, Michelle Q. And good afternoon, Stephanie I. And good afternoon, Emily H. And okay, and who else did I miss? And Freddie. Good afternoon. Well, he can't hear me yet. Okay. All right. So we have much to do. So thank you again for your indulgence. Monday, it was a great pleasure to meet. Yes. Thank you for the direct chat. Yes, yes. That fair enough. That is. Thank you for the reminder in the direct chat. There's only one direct chat, so if I'm talking to you, I'm talking to you. Yes, promise. Yes, yes. My agenda today, the main part of my agenda is to say things that I hope will help with Lab 3. And by request or well, yes. Okay. So I have things that I have material to give that is in the hope of connecting to and clarifying Lab 3, but then also hopefully I'll leave time. Hopefully there will be time. Um, Even after I give like a speech or a lecture material that is meant to help people with Lab 3, then I definitely will encourage questions. I mean, you can really whatever you can just even whatever you can ask. You should ask questions whether it will for to help your um post lab or your formal report, et cetera, et cetera. So that is yes, that is a big agenda item for today. Good afternoon, Victoria. And again, and it was really a pleasure to meet some of you in person on Monday. Really, it means a lot to me. And I hope that happens again or whatever. Okay, so yes, Lab 3 is a big item, is a big agenda item today, but we have a couple of other agenda items also. One, I said in the posting that said we didn't have class yesterday, I said there would be a video posted like at some point, and then once the video is posted, then you make comments on it and you get more points for doing that. That's all true. I have not posted the video yet, so it's on me and I'm a little bit behind. So whenever that happens, then you just do that and you get points for it. But there's nothing you can do until the video is posted. You can gently remind me by text. That's totally fine. But yeah, anyway, so that's that. Then also quickly, this is important. I'm going to try to be quick about this. I'm okay. I'll put this in the chat. I will do an official posting in Google Classroom about what I'm about to say, but just in terms of the midterm exam, which of course we have to have one. So the logistics and the details will be in Google Classroom, but as a heads up right now, I'll put this in the chat right now. Hang on. Today. Yeah. Oh, someone else is here. Wait, okay. Hold on. I'll clarify that, or I'll Yeah. Okay. Oh, thank you, Shawnee. Okay, that's helpful, Shawnee, that acknowledgement. Okay, cool. Okay. Oh, thank you. Okay, and I'll be more clear. Thank you both for like acknowledging that this communication is getting across. This is not the last thing I'm going to say about it, of course, but I don't want to say too much about it. Hold on, one last thing. Okay. Okay. So again, just so that you have this information, because I know you need it and deserve it. What I just put in the chat, I will also put in Google Classroom, like in writing, but the bottom line, as I guess you can see, I guess Fariel and Shawnee can see, like the exam itself will be due right before class starts on Monday, not this Monday, but a week from this Monday, if I'm saying this right, I believe, yeah. So the exam itself will be posted the Thursday evening prior to that. So you have like all, Thursday night, Friday night, and all weekend to work on it. It's take home, it's open everything. You can use your notes, you can use videos, you can talk to friends, blah, blah, blah. If you've never had me before as a professor, I will make more clear like how that works or why or what the expectations are, what it means to cheat or not cheat. We'll talk more about that, but many of you know. I mean, if you have had me before, same deal as 203 for good or for bad. Um, um, so yeah, and there will be you'll as far as what's on it, well, what it's on, it basically covers all the material of simple harmonic oscillation, all the material through homework 3, which is also an agenda item for this week, to give you quick answers to that. But you'll get a practice document. As many of you know, you will get a document that's very similar to the actual exam. You'll get it in advance. Some of it will be solved, some of it won't, but you'll get it in time to like ask questions or discuss next week. So that's how you prepare for the exam, is through the practice document. So hopefully that's enough information for now. Oh, people are here, sorry. So I'm just saying that so you can plan and you can know. We'll talk more about it next week. But that's okay. That's the bottom line of that. Okay, wait. Oh, sorry. Yeah. Sorry. Thank you, direct chat person who's looking out for her friend, their friends, his or her friends. Okay, thank you. Yes. Okay. Friends might be a loose term. Okay. So that's the exam answer or and again, also just again, like the point is we'll talk more. I'm strict about exam submission deadlines. Like that's not like homework. That, especially if you have all weekend to do it and it's open universe, one thing that is strict about it is you got to turn it in before class starts on Monday. That is the rule for the class, and it's real. But on the other hand, if you have personal things, if you already know in advance, there's a whole personal issue that you have. Well, no, let me back up for a second. I'm doing all this. If a number of you know that this like conflicts with Orgo or something that really affects a number of you, let me know in text. I don't want to have a whole negotiation right now because we have too much to discuss about Lab 3 and things. But if I just made a decision that like globally like messes everybody up, you can gently and politely let me know with some other means, like in texting or email, and I will take that into account. I'm not trying to conflict with your other professors, believe me, and especially if they've already posted it in the syllabus weeks ago, I will defer. That's number one. But number two, if it basically works for people this timing, like all things considered, but then you have a personal issue, that's different too. You can personally communicate with me, and if we have to work something out, maybe we will. but that doesn't have to affect the whole class. As long as but you have to communicate with me. The exam, if I don't communicate with people on an individual basis, I'm going to assume that the deadline is 12/15, Monday, the 24th, and that we have to be strict about. Okay, that's it on the exam for now. That we can talk much more. Yeah, wait, wait, funny. Wait, I don't even know if that's a joke, but yeah, I guess what Chris and Katie's saying. I don't even, but yes, but that's right. Okay, I think it's right. All right, so that's that again, and you can remind me to post that in Google Classroom to make it more clear. You can also gently remind me this weekend if you want, like if you don't see practice documents getting posted this, because I'm a little frazzled as always. So if like Saturday comes and you don't see practice materials, you can gently like reach out to me and just say politely, like, oh, if you get a minute, can you? Okay. So that's that. All right. Now, lab 3 is my main thing, But one thing I want to do before, yeah, very quickly, the last thing I want to get out of the way before I get to the lab 3 material today, I'm going to shut up. Right. Thank you, Michelle F. She's totally right. As though it didn't already happen. I'm going to shut up. We'll see. On the next page, I'm going to quietly write out answers to homework 3. I'm going to write out answers so that you can check your answers so you can check, because I think at this point, now that we've like spent so much time on homework 1 and homework 2, if the differential equation concept is beginning to sink in, then by the time you get to homework 3, it's kind of a straightforward exercise. I'm not saying it's easy material, but I'm saying once you get the material or once you've really practiced it a lot in homework 2, then homework 3 is kind of an exercise. So I'm going to write down the answers and you see like how you feel about them, but I'm just writing down the answers. But I'm also going to say, you'll find frequently on the midterm exam, of course, is like a bunch of long problems, like stapled together that you do solutions to the problems according to the 5-step method, right? Well, generally speaking, on the midterm for this class, one of the problems in the midterm looks a lot like the sheet of homework 3. Generally speaking, homework 3 essentially appears as a midterm exam problem. So you do want to know it. And I'm going to tell you right now, again, before I shut up, on the exam, you want to do it fully out, like with 5-step method and all of that. Like you need to show that you understand it. Now, I'm not going to do that right now. I may post a video about that, and I'm sure there are old videos about that. Right now, I'm just going to give you the answers to see so that you can check to see if you know what's going on. But please do make a note somewhere that of all the problems to like practice that to see whether you understand them and to practice like writing out a full detailed clear solution. Homework 3 would definitely be a good one to practice. Now, but now that said, I'm just going to write down answers. I'm not saying you can't ask questions about them, but just know they're just answers for right now for you to check. Well, okay, a little bit more than answers, but I'm not doing full. I'm going to give, you do need a diagram for homework 3 for sure. You have to do the 5-step method. So it has to start with a diagram and all that. I'm going to give you the diagram right now. I'm going to flip the page, but well. Well, in fact, okay, I'm going to flip the page, but tell me if you need me to go back. I believe that's the answer to number one. Like, how much time does it take to go back to its initial temperature? That means what's its period? And I believe that's the answer. Again, you have to write much more than that to get full credit, like in the homework or the exam. So we can talk about that. And if you want to make a note as something to talk about, like next week, that's fine. But I believe this is the answer. Again, just for checking. Okay, and I'll go on. Hold on, sorry. I forget what the next. Oh yeah, okay. At the very least, I suppose I should have said, I mean, so the question for this one was, what is the period? That was the question, but okay, and that's the answer. So this one, the question is, what is D at 200? So okay. So the answer for the second one, the temperature at precisely 200 seconds is approximately 127 degrees. So I'm just, that's a plug and chug. I'm plugging into the cosine function, but just one, but your calculator has to be in radian mode to get the right answer here. We're in radians. I'll also say quickly, like the key, and again, for the question number one, you have to show a lot of work, but the key to the whole work of question number one is recognizing that if you just stare at that differential equation, it is the differential equation for simple harmonic oscillation. And the angular frequency for that simple harmonic oscillation must necessarily be the square root of that constant, like the square root of 121. That's where I get omega equals 11. I'm saying omega has to be the square root of 121. That's the key to the whole thing. But that's the thing, therefore, you have to spend your time explaining. Like, in fact, I'm going to say this again. Pro tip, when I say explaining, and again, you can ask me for more elaboration on this next week or something like that. But when I say you need to explain it more, I'm to the point where you should take two derivatives to show that that's true, like you do in the exercises of homework 2, to show that omega has to be the square root of 121. But anyway, but those are the answers so far. Yeah, I'm not looking. Oh wait, I am looking at the chat. Oh, can I quickly go up? Sorry, can I quickly go back to page? Hold on. I think that's the page you want. And also I'm looking at the chat. Yeah, so that's a really good question. So someone else is asking in the chat, is it radian mode for like all? Oh, okay, great. Is it radian mode for all the other questions? Like totally yes. So for anything that's about simple harmonic oscillation, you're always in radian mode. Yes. Anything that has to do with these cycles, omega, frequency, anything to do with these harmonic oscillation, which is the subject of the whole exam, yes, you have to be in radian mode. The only reason I'm pausing on that is just to be clear, on those dot and cross product exercises that you did at the end of homework 2, those are super important for later in the course. And those angles those are not about cycles. Those are about like geometric angles. So they tended to be given in degrees. So for those, you would be in degree mode, not radian mode. So that's a little bit confusing, but those are not, unless I'd say otherwise right now, that's not the focus of this exam, put it that way. So yes, anything that's about harmonic oscillation, you're in radian mode. Yes. Okay. Sorry. Okay. So cool. Okay. So I'm almost, so therefore, and on that note, then question 3, it says what are the units of the 121? It's not a trick question, but it is a tricky, the answer to that is, well, the answer is 121 equals omega squared. So the units of 121 equal the units of omega squared, which is to say radians squared per second squared. That's the answer. Quick point on it. So, okay, really quick point on the answer to question 3, what 3 is really getting at is, even though this whole question is about temperature, and even though like lab 2 is all about pendulums, and even though lab 1 and homework 1 is all about masses on springs, even though the units of the variable that's oscillating could be all kind of different units, it could be meters, it could be radians, it could be degrees Celsius here, whatever. The constant in the differential equation is just omega squared. That's a cycling rate, no matter what kind of value is cycling. So the 120, so the constant omega squared is always just in radian squared per second squared. That's the answer. But then also a technical point that's sort of worth knowing. I mean, because otherwise you can get confused a lot of times with the unit cancellations in other calculations. It's important to note that radian is a real thing, and radian, yes, we prefer over degrees. But radian is not actually a proper unit of SI or MKS or whatever. A radian is not, it's an important word and it's an important concept, but it's not strictly speaking a unit, because because an angle is a ratio of arc length to radius. An angle, I keep saying over and over, is really literally a fraction of a circle, or to physicists, a fraction of a cycle. So an angle is a fraction of a circle, and that means literally a pure fraction, a pure dimensionless ratio. It's a ratio of meters to meters. How many meters to how many meters? So the meters cancel out. So strictly speaking, a radian does not, it's not actually a unit. And let me say one last time before I go on. If you might say, well, wait, it's a unit, but it's not a unit. It's a unit, but it's not a unit. It's a unit. It is, it's a description of what we're measuring. We're measuring angle in chunk. It's an increment of angle measurement, and it's the best one. But when I say it's not a unit, what I really mean, if you think about it, is what is a standard unit of MKS or SI? Like, what is a standard meter or a standard kilogram or standard second? First and foremost, with each one of those is a specific size. The kilogram is a certain mass, right? The meter is this long. A meter is a unit of length that is this long, but a radian is not any particular size. It's a portion of a circle, and the whole essence of it is that it is that portion regardless of how big the circle is. Okay, so sidebar, but the reason, so either answer would be acceptable here. You could say radian squared per second squared, or you could just literally say 1/2 squared. But the reason I'm saying all this is a lot of times when you're converting back and forth to hertz and things like that, a lot of times we just like, you'll see that the radian just like casually goes away, and it might confuse you. And the reason that a lot of times the radians just casually go away or casually get introduced is because they are not strict units in the way that meters, kilograms, and seconds are. Okay, anyway, that's enough on that. But that's the answer to number 3. And then I'll shut up again. I'm just going to do the answers for the rest. Wait, I'm looking. Okay, the chat. Okay, 4. That's the answer to that. Okay, so very quick. Again, you can ask questions, but my answer to 4 is just like, if you pretend this thing is a spring, then how stiff is the spring? And the purpose of that is what, from here on in, anything that is a harmonic oscillator, whether it's a pendulum or it's a weather system or it's electric field, we're saying from now on, harmonic oscillators are anything that has the same mass as a mass on a spring. So all oscillators ultimately act like masses on springs. So we can always think of them as masses on springs. So even if there isn't actually a piece of metal coil, we can always think of like, if like how stiff is this effective spring or this like analogous spring. So that's what we're doing here in question 4. In question 5, 6, and 7, the answer to all of them is false, but they're kind well, wait a minute. Oh yeah, the answer to all of them is false, but kind of for stupid reasons. Like, let me put it this way. Well, the answer to all of them is false. But let me give you an example. But what would have been true? I'll go to the next page. What would have been true? Like, what's an example of something that would have been true? The most straightforward true answer, the one that we're really looking for, would have been D. The straightforward true answer would have been D equals 200 cosine 11t. Like, that would have been true. That's really what we're looking for. But also, just to keep it clear, what would be an example of something that might be more tricky or less obvious that would also be true? This would be true. If you think about it, like, and why do I say that? Well, because remember, we've shown now that you can introduce phase constants, and still make the differential equation work. And if you differentiate this twice, you will see that you do get this. Like, true or false means if you differentiate it twice, do you get the original differential equation? Again, it's back to like the exercises of homework 2. So that's an example of something that would have been true, but just wasn't given. All right. I believe that's, so I want to get to, it's 12:45. All right. So I think we're doing, so I'm looking at the chat. As far as I'm concerned, that's the end. That's homework 3. Actually, I mean, it is homework 3, but I'm going to do one more thing. Because we are fine on time, actually, we're, which I appreciate. Let me give you a slightly better, at least roadmap or idea of what I'd be looking for in question 1 of this homework, because question 1 is like the big deal. And again, if this problem were to appear on an exam, and let's say, especially if this problem were like one of the first problems you did on the exam, you would really want to use it as an opportunity to show that you really understand the math and physics of simple harmonic oscillation. So, and then if things repeat later in the exam where you're using the same concepts again, you don't have to spend as much time establishing them. You could say, like, refer back to page 1 or whatever. But what I'm getting at is this. Okay. So first of all, in step 1, when you do the diagram, for question 1, stop me if you don't know where I am, but when you solve question 1 of this homework and you do step 1, you'd have to provide a diagram, and which would be a cosine. Look at the diagram I provided 2 pages ago. Like, the purpose of when we do graphs in physics, we don't do every single point. We don't do a dot to dot or connect dots. The 3 key things we're always looking for in a graph, you could write this down. The 3 key things we're always looking for is axes that are labeled, a clear trend or shape, and at least one value that is identified so that we can get a sense of the scale of the graph. So once you know the shape and the scale and the axes are labeled, then you know what the function is. Like, those are the 3 ingredients of any graph. But the purpose of so you would want those, as I did 2 pages ago. But then any diagram that you're ever putting down to solve a problem, the purpose of the diagram is that the labels in the diagram are defining what constants and variables you're using to solve the problem, right? So the whole purpose of this cosine graph that you would provide in a problem like this is it's got to label capital T and omega in the diagram, because you're going to use them to solve the rest of the problem. So you show in the cosine graph that by T, what you mean is the interval from one crest to the next crest, the interval in time, because the x-axis measures time, right? And then you write right in the graph, you label T like I did, and then you say, by definition, omega equals 2 pi over T, right? And that is now so angular frequency equals number of cycles per unit time, where cycles are measured in radians. Follow? So number 1, step 1 is to provide a diagram, even if the problem didn't give you a diagram. And the purpose of the diagram is to label all those constants and variables that you're going to use in the math. Then step 2, the question. What is the question? The question was, in effect, what is T? Although you should explain that. Like, the question didn't literally say that, but that's what the question means. Now, step 3, the GDPs, where you're going to spend much more time and space than I did 2 pages ago. What am I looking for in step 3 GDP? I'm looking for something like this. This is a roadmap. Even this is not complete, but in general, if you want to back up and introduce like a generalized variable called z. Like notice I just switched to z. It's not a typo and it's also not meant to confuse you. But this is a step 3 when you're going in general. So in general, you back up, you say like, say we have any variable z, then if that differential equation applies to z, then the solution to that differential equation is z equals z naught cosine omega t, whereby omega, what I mean is da 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 da. And omega, and you explain it in math and in your own words. Like if you have that general differential equation, then that is the solution. And the angular frequency in that solution is the square root of that value, of that constant value that was in the differential equation. Like you explain that and how, and you show, you could say like, why, how do you know that? Because if you differentiate z, the z that I just wrote down twice, you do get back the original thing. Like walk me through that in step 3 GDP. You're trying to show how you know that there's a cosine function that you're going to use to plug in for the rest of the problem, and how you know that the omega in that cosine function must be the square root of the original number in the diff EQ. And you're trying to show that you understand what omega means. Like that's your job in step 3 GDP. So this is like a little roadmap of that. Okay. And then in step 4, you plug in the numbers like we've already done. Okay. So that, again, if you want to ask more, I'm not trying to rush you. I'm trying to rush me. So if you want to ask more questions about that, either now or next week, please feel free or make a note. But that's what I'm looking for. That's homework 3. That's an exam problem generally. So now, if that's okay, I'm looking at the chat. I think I'm looking at the chat. If that's okay, I'm going to shift gears entirely now. Yeah, we've got 40 minutes, 38 minutes. I'm going to shift gears entirely now. Okay, so pause for a second. Give me a second. Oh, that's not what I meant to do. Okay. So here's the thing. Once we get into lab 3, all of a sudden, you're making waves. You're looking at waves. Now, I have to give you some rigorous definitions of exactly what I mean by waves. Like what exactly is a wave is kind of like the point of a lot of the rest of the course. But on an intuitive level, I know that intuitively you all saw that you were sending ripples back and forth across this long spring. And those ripples we call waves. First of all, I want to make clear that yes, lab 3 is the first time you're ever actually looking at waves or wave motions or wave equations or anything like that. Part of the reason people are confused when they go into lab 3, and they always are, and it's a lot, lab 3. But point number 1 is not once up until that point, nothing we've been saying in lecture is about waves yet, like until this moment. Everything we've been saying in lecture is about simple harmonic oscillation. A simple harmonic oscillator is not a wave. Let me make that clear first, because people get this. This is very confusing or sometimes. This is what we've been studying, or this, or whatever, or even this. Like we've been studying behavior that goes back and forth, where a variable goes back and forth in time in a cosinusoidal fashion. That is not a wave. Even the graph of a cosine function, that wiggly shape, that graph, that is not a wave. That is a graph of oscillation. In lab, you're suddenly looking at waves. Now, the reason you're suddenly looking at waves, well, because we totally care about them, but wave is built from oscillations. Oscillations are the key ingredient to waves. So you can't have waves without oscillations, but you certainly can and do and have had many oscillations that don't have waves, right? So first of all, everything we've been doing for 3 weeks or 3 homeworks up until now has been the key ingredient behind waves. What you're trying to see in lab 3, so in lab 3, you suddenly introduce a wave. And what we're actually trying to do is break down that wave into data sets that show how its ingredients, its fundamental ingredients, are oscillators. That's what's happening. You're decomposing a wave and seeing that it consists of various oscillations happening together. Okay, now I'll be more specific now. But again, one takeaway, first of all, is all waves must involve oscillations, but not all oscillations are waves. Okay, so what's the relationship? What's the difference? What you were doing in lab 3, so you were, well, all right, so. Well, okay. Okay. First of all, I'm telling you something you already know. I'm just like summarizing. It is stop me at any more. If I say anything about what I think your experience was, but you had a different experience, like obviously tell me. But here's what I think happened. You and your lab partner like stood apart from each other, and you're like shaking your medium up and down and sending these pulses back and forth until they're like falling into a pattern where they're going like this or something like that. And you're seeing this pattern of ripples propagating or pulsing back and forth and ultimately up and down on the spring that we call a medium. And you took a video, right? And then you put the video into Logger Pro. And then you started putting red dots, right? Superimposing or whatever, red dots onto the video. But you put the red, now here's where you need to stop me if I'm not making sense or something. In my understanding, you put red dots on your video 2 different ways. Like you did it in 2 different processes. And the difference between the 2 processes came down to this seemingly stupid technical thing where for one process, you checked a box in the settings. You checked a box that said something like allow multiple points per frame or something like that, right? Allow, and again, stop me if I'm wrong, or maybe even tell me in the chat if I'm right that this happened. Like there's this checkbox under settings, under certain video settings or whatever, that said allow multiple points per frame. And one way you made the red dots, you had to, thank you. Awesome. Thank you, direct chat person. That totally submit that for points. Thank you. So one way you had the box checked and one way you didn't. And maybe you understood what you were doing when you did that. Maybe you didn't. Let me tell you what you were doing when you did that. When you, oops, when we did not allow multiple points per frame, then what that meant was that every time you put a red dot, the movie would advance by a frame, right? Like you put in a red dot somewhere, and then automatically you had no choice but then to set your next red dot somewhere in the next frame of the movie, right? When you had the box unchecked. And where were you putting these red dots when you did this? What you were doing, if you were doing it right, was you were looking at your movie, like you're looking at, like you froze a frame of the movie, so you had this like squiggling thing. The rope, the spring was squiggled across the room, and presumably, if you did this right, you had some kind of like vertical reference line that you kept your eyes fixed on. Maybe it was a meter stick behind the rope, or maybe it was a edge of a wall or something, but there was supposedly some kind of vertical reference line that you were bearing in mind. And when you were doing this data set, you would create a dot wherever your slinky intersected with that reference line, right? So like in this case, I put a red dot right here. And again, stop me if I'm wrong or tell me if I'm right. But then, so you'd put a red dot right there, and then automatically under this setting, the movie would advance. So then the whole spring would be in a different position. So then and again, you would put a red dot where the slinky was intersecting with the vertical line. So if in the next frame, the slinky was like up here, then you'd put a red dot there, right? And then on and on and on and on. So you ended up, for this data set, you end up getting a whole bunch of red lines that are all at different vertical positions along some reference line. Again, please say whether it's the same person as before or just someone in the direct chat, just say like, I'm still with you or whatever. Okay, great. Okay, that's honest. Okay. And you're okay, cool, awesome. All right, great. So now what the heck are you doing? Like, what are we doing when we're doing? So you end up getting this bunch of red dots all in a vertical line. And then you create a table of value out of those. A table of values. You created a 2-column table if you did this right. And then from that 2-column table, presumably you created a graph. And by the way, ideally, hopefully, you went to some other piece of software to create the graph, like Desmos, I hope, or Excel. But in any event, you created a graph out of this data. Now, this is one set of data. Now, what is all this? If you think about what you were doing here, by not allowing multiple points for a frame, by having that box unchecked and always putting red dots along some vertical reference line, what you were doing here is you were in effect holding the horizontal position that you were staring at fixed. Like you were fixing some value of X fixed as a constant in your mind. And what you were doing, since the movie was advancing a frame every time you put in a red dot, you were putting in a different red dot for every different moment of time. Like, right? Like, and I don't know if it's every second or whatever number of seconds there are between frames, maybe 1/60th of a second. But basically what you were doing was you were charting, you were taking a bunch of data that would show, well, okay, I'll put it a different way. What you were charting here was time as your independent variable and vertical position, Y, as your dependent variable. Like that's what you were doing here. You are getting data to ultimately answer the question, how does vertical position depend on time, assuming that I hold horizontal position constant? That's what you were doing for this. I'm going to say that again. Or like you were picking a particular value of X, not a special one. Like, you could have done this whole thing with a blue reference line that was somewhere else. But once you picked it, you never strayed off of a certain horizontal position, and you just clicked through the movie. And at every 60th of a second or whatever, I guess however many frames per second there are, I forget, 30 frames per second. At every 30th of a second, you're asking, how high is this section of the spring? So you're getting height as a function of time for the spring at a given x. You're getting y as a function of t for a given fixed constant value of x in this data set. And then you got a graph from it. Are you with me so far? I'm just going to pause for a second and look. Could just anybody else just say if they're still with me? I know I'm being weird, but if I'm going to try to help, I really want to try to help. So is anybody still with me? Does this, yeah, okay, thank you. Awesome. Okay. All right. Awesome. Okay. Now that once you turned it into a graph and stuff, you probably noticed, maybe surprisingly, maybe not. And thank you. Oh, great, Brooke. Okay, thank you. What you notice is that function, y is a function of t, you notice that you got some kind of, like once you put it on a graph, you got a cosine function. Maybe surprisingly, maybe not. Now, and let me be clear, that cosine function that you got described what your red dots were doing in time. Put another way, so far what I'm saying is you got a cosine function to describe t as input and y as output. So what that says right there is that any little section of the larger spring, any sliver that you picked, is itself acting like its own little oscillator, right? In other words, you're saying that the red dots, that they're not just going up. It's not like, in other words, what you're not finding is that every second the red dot is 2 centimeters higher. It's not a linear function. It's not like every time the movie advances, the red dots are 2 centimeters higher or something, and they're not going on up forever. What you're finding is that the red dots are going up, and then they're going down, down, down. They're going back to here, and then they're going up, and they're going like slower and slower as they get closer to the top, and then faster and faster as they go down. Like you're finding that any sliver of this spring is its own little individual time oscillator. It's obeying the cosine function if we hold x constant, right? But then, so any little section of the spring can be viewed as its own vertical spring, as its own little individual oscillator. But that means any section. So there's like a bunch of them all doing something at the same time, right? So in fact, I'm going to pause one more second. So already what that is saying is that what is this whole wave? In effect, it's like a oscillator next to an oscillator, next to an oscillator, next to an oscillator, right? That's what you're already seeing once you get this data set. That a bunch of oscillators next to each other, all doing the same thing, but all staggered in phase, is making this ripple effect that you're sending across horizontally to your partner. But then that's not the whole story. That's a big piece of the story. But the other story is that then, so this is one finding. But then the other thing is then you checked off the box. So then when we so we can call this, or finding number one, whatever. Call it finding number one. Not that it doesn't matter what order you did this in, but this is finding number one. Then for finding number two, we checked the box, or we unchecked the box, and we did allow multiple points per frame. Right? So what does that mean? So for this one, you looked at your spring, here's your spring, and you put a red dot somewhere at some height, but you put the red dot in, but now this time with the box being unchecked, now when you put the red dot in, the frame doesn't advance. The frame just sits there and it asks you to put another dot in. So you put so where do you put the dot? You put the dot at the next place that you see spring. You're always putting red dots on metal, right? Like in the other data set, you put a red dot every time the metal intersected with a reference line. Now here we don't use a reference line. Here we just put red dots, as many as we want, in this one frame, all on the metal. So what are we doing here? Here, we're not using a reference line, And we're not letting the clock tick. We're not putting a different red dot at every different second anymore. All of these red dots that we're putting here are all at the same second, the same moment of time, right? So here in this case, when we've checked that box here, what we've done is we've picked a particular value of t and held it fixed as a constant. We're picking some arbitrary moment in time, holding it fixed. So we're just looking now at a frame, right? Not multiple frames, not a movie anymore, but a snapshot. We're just looking at a moment of time. And now we're asking, now we're tracing red dots and saying, how high is the metal over here? How high is the metal over here? How high is the metal over here? And what do I mean by over here? I mean, I'm letting my eyes walk across the picture now. Instead of letting time advance, I'm letting horizontal position advance now in this case. For every new X position that my eyes look at, I ask, what is the Y position? For every new horizontal coordinate, I'm asking, where is the metal vertically? Right? So this one, you're holding time constant, but you're finding out how vertical position is a function of X. Do you see what the other one was hold X constant. What is Y as a function of T? This one is hold T constant. What is Y as a function of X? And this time, of course, I mean, it's staring you right in the face. What you get here again, well, here you get, of course, a cosine. I don't mean of course, but here you can see, in other words, this one, literally, once you turn the red dots into a table of values, and now your table of values is X versus Y, not T versus Y, that table of values you then throw into Excel or Desmos, and it spits out a graph. And of course, the graph now, in this case, literally looks just like the shape of the picture that you're looking at. It's not a coincidence, because time is not involved anymore. So now you're literally asking for a relationship between this part of the grid and that part of the grid. So the relationship was staring you in the face the whole time. It is just that cosine curve that the actual metal is actually sitting in at a given moment in time, right? So this time you get, again, y equals some other a. We can call it a2. Well, it probably is, well, whatever. Maybe, technically, the other one was like a1. And this one's a2. This is another cosine, but this one is cosine of some constant times x plus some other phase constant, call it phi2, right? So I'm going to fill in that space in a second. But for the first thing I'm saying is the first key finding, and it is a deep point. In a way, it's really simple, but in another way, it's not easy. What we're first of all saying is, okay. What first of all I'm saying is that cosine shape itself, the cosine shape that we have been attributing to oscillation, that cosine shape describes oscillation. A cosine is not a wave. A cosine is a frozen wiggle, right? That cosine shape, that cosine shape is not a wave. That becomes a wave if that cosine shape starts wiggling up and down. You see what I'm saying? Right? Or put another way, what is a wave? A wave is cosines happening in time while cosines are happening in space. A wave is a superposition of space cosine onto time cosines. Put another way, or what I'm put the way you did in the lab. If you look at any individual x value of a wave, you find that y is oscillating cosinusoidally as a function of t. So if you look at any position x, you see that that sliver of the wave is being a harmonic oscillator. But conversely, if you freeze the wave, you see that the whole physical shape of it, the whole spatial shape of it, the vertical space of any section of it as a function of the horizontal space, that the whole space of the wave is a cosine. Neither by itself is a wave. This shape is not a wave, and this motion is not a wave. But when you put them together, when you either have a bunch of these next to each other, that's a wave, or you have one of these space cosines. So in other words, if you take y equals, I'll say it one last time and then I'll move on. If you take y at cosine of x and you start cosinusoidally wiggling it in time, then you have a wave. Or if you have y equals cosine of time and you spread it out in space, then you have a wave. But a wave is literally that. It is harmonic oscillations in time while harmonic oscillations in space, or it's harmonic oscillations in time arranged harmonically in space. I mean, it's truly a fascinating thing that nature can do this. Okay, but so first of all, the big takeaway of the lab that you're trying to show is what I just said. You're all of these graphs and all of this stuff, and maybe put in obviously I still have more to say, and I'd like to answer questions, maybe if I can, or if not today, Monday. But like, hopefully this is the big picture. Okay, wait. This is the big picture. Is that a wave is cosinusoidal harmonic oscillations in space superposed on cosinusoidal oscillations, harmonic oscillations in time. When you hold space fixed, you get y equals cosine of t. When you hold time fixed, you get y equals cosine of x. One thing though now, there's got to be a term right before the x. In this cosine, in this second finding, this thing for what happens when we hold t constant, there's got to be some kind of letter right before the x. Otherwise, the units don't work. Right? You can't take the cosine of a meter. So just like before, you can't take the cosine of a second. So we put a constant before the t, and it was some kind of cycling. We put omega. And omega was measured in radians per second so that the seconds canceled out and you're just left with radians, right? We had to do that. And so that omega was how many radians per second you're oscillating. It was the rate of cycling per time. Well, the same thing has to happen here. The same type of thing has to happen here. There's got to be a constant before the x. Now, it can't be omega. It can't be that same constant. Omega is measured in radians per second. We're not trying to cancel out seconds here. We're trying to cancel out meters. So there's some other constant that goes here that turns out it's called K. And this is very confusing. I didn't make this up. It is K, but it's not the same K as Hooke's law. So I draw it with serifs on it, like draw it anyway, or you can make it a lowercase or whatever if you want, but there's some other K that goes here. But the K that they're talking about in the lab, and K, I'm going to say this too if I run out of time. Generally for students, for people, one of the really confusing issues of the lab is what is K, like K, all of a sudden they're talking about K, and a lot of people think it's the same K as Hooke's law. It's not. So first you get over that hump and realize it's a new K. Then you've got to start with, what is this new K? It's out of nowhere. We never talked about it in class before. We're talking about it in class now. This new K is like a cycle. K is the space version of omega. K is to space as omega is to time. What do I mean by that? I mean that K is the constant that has to be stuck in before the x, so that the meters cancel out and we're left with radians. So whatever K is, it's measured in radians per meter. Radians per meter. Just like omega is measured in radians per second. K is measured in radians per meter. I'll go to the next page here. What does that mean? It means it's some sort of cycling rate, just like omega was, but in time. What K measures is how many radians, how many cycles are there for each meter? In other words, how rapidly are the crests coming in space, not in time? How close together are they? How far apart are they? It's literally whatever you are ever understanding about omega, which I know many of us are still just getting now. I know that. Omega, just as omega. So homework 3, and the other problem I was doing was really looking at omega, radians per second. Now we're saying once you introduce waves, waves are space plus time. So there's a factor that we call K that is measuring the same idea, but in space. How many cycles are we fitting per each meter? This thing K is called the angular wave number. It's like the number of waves, the number of wave crests that you see, not per second, but per meter, right? And just like, and it's measured again, it's measured in radians per second. And just like omega is 2 pi over period, right? Like omega is radians per second. It's how many cycles are we doing measuring radians per unit time? Well, just like omega equals 2 pi over t, we can say k is 2 pi over, well, I'll write it like, well, yeah. Just like omega is 2 pi over t. Well, actually, let me pick this, where t equals time for one cycle. K is 2 pi over lambda, where lambda, here, hold on, let me make this perfect. And not perfect, but I mean, hold on, I'll make the parallel perfect. T is period, right? What does period mean? It means time for a cycle, time between one crest and the next crest. Well, lambda stands for wavelength. You've heard of this, since 6th grade, but lambda is wavelength. That means space or length or distance for one cycle, right? So, well, I'll go back. If anybody asks me, I'll go right back. But so, like in terms of graphs, right? If you have if t, capital T, is the period of time for a full cycle, the period of time between two crests, then t is that interval on a yt graph. But if you have a yx graph, then the interval between the two cycles is not time anymore, it's space. And the length, the distance between two crests in space, we call wave length, the length of the wave, and we designate it with the Greek letter lambda. Well, just like period is in effect the reciprocal of frequency, wavelength is the reciprocal of wave number. Bottom line again, I mean, there's a lot of information in a way, but the bottom line of what I'm saying right now is that K is to space as omega is to time. That's what I'm saying. Omega measures radians per second. K measures radians per meter. Omega is in effect the reciprocal of period. K is in effect the reciprocal of lambda. I say in effect because then you have to multiply by a factor of 2 pi because we're doing all this in radians and there's 2 pi radians in every cycle. Okay, so that's what those letters mean. And we still have 5 minutes. So again, conceptually, what we're saying here is a wave motion is harmonic oscillations in space superposed onto harmonic oscillations in time. I know I have 5 minutes. So the reason everything's about these two graphs and these two data sets is because a graph, what you've been doing in science and math your whole life, like A graph is necessarily input, output, right? A graph has two axes, two dimensions on a piece of paper. So there's one input and one output. The reason this is the first lab you've done in a while where the actual picture of the situation cannot be captured in one graph. The reason we need two graphs here is that what we're ultimately saying is a wave. If I keep saying if a wave is oscillations in time and oscillations in space, and let me be more specific, I'm saying like what we're saying is at any given moment, if you, sorry. What we're ultimately saying, the nature of a wave is if you walk in and say, and you're watching your two lab partners like make the ripples go back and forth, and you go, wait, how high is the metal? If you just say, how high is the metal? One of the lab partners will have to say to you, you got to specify your question better. When you say, how high is the metal? If you want me to answer, how high is the metal? You got to tell me two things. You got to say, first of all, where are you looking? Like, where? How high is the metal over here? Or how high is metal over there? Like, the answer will depend, right? But also you got to tell me, when are you asking? If you tell me those two things, if you say, I want to know where the metal is, how high the metal is at this moment in time, and at this horizontal position, then there's one and only one output for those two specifications. In other words, the wave equation or a wave function is a function of two independent variables. There's one dependent, two independent. That's why you needed two graphs. And we're saying that both those graphs are occurring at the same time, but we couldn't put them in one picture unless we literally had a cube or something like that, okay? So a wave is our first example in physics and in math, really, where we have a function, we have an output based on two independent inputs. And I'm just about to wrap up. What you did physically when you held one thing constant like t, and then you looked how y varied in x, or then you held x constant and you looked at how y varied in t, what you were physically doing a version of what we call in calculus partial derivatives. So I'm just going to write this. We'll obviously practice with this more on Monday and stuff like that. I know I'm leaving you with a, but if we write something like this in physics or math, if I use d's in this funny way, if I write these funny little like look like backward sixes, they're pronounced. This is called a partial derivative. The partial derivative of y with respect to x would mean take rate of change with respect to x, holding t constant. Like it's the mathematical version of what you literally did in the lab. If you take in other words, if you have any function where there's two variables, to take a partial derivative means hold one of the variables, treat it like it's just a pure number, and do the derivative with respect to the other. So we have 1 minute. So just really quick example. Say you had the function y equals 3x squared plus 5t cubed, right? A function of two variables now, because that's what you have here now. Like if you had that, then to take the partial derivative with respect to x would be to say, would be to go 6x plus 0. It would be to treat t like it was just a number, and therefore that whole thing, 5t squared, 5t cubed, is just a number, so its derivative is 0, right? Or if you do dy dt, you would get 0 plus 15t. Punchline, I know it's 1:30. What we're ultimately concluding is what you saw in what a wave is. A wave is a function of two variables. It is a cosine in time while also being a cosine in space. So the kind of derivatives we have to take of it are partial derivatives. That's what's going on in the whole analysis. But to take those partial derivatives just means doing a derivative one at a time, treating the other variable as a constant. I will say more about this on Monday. I know your post lab is due. So hopefully this helped somewhat, but then I will say more until okay, so I know you have to go. So bye, but I'm staying here to answer questions. Sorry, but have a nice week or a nice weekend. but I'm still here. Thank you. Thank you. Oh, thank you. Okay, awesome. Thank you. Awesome. Oh, you okay. Thank you. Have a nice day. All right. Sorry. I'm still here. If anybody has questions about stopping the recording, hold on. Yes, have a nice day. Okay.